So, let us what we have done is we have just formulated the integral equation, we have not yet come upon how do we actually solve it. So, now we will look at how to solve it, and we will see that solving this is actually not that difficult, at least in this case. So, let us see what. Okay, so let us draw this once again. So, this was my z, x, y. Okay. As with any system of any equation that you see, the first strategy to solve it is to discretize it. So, we will follow the same thing over here. My variable is rho of y. So, I should discretize along the y axis, right. So, what I will do is I will discretize it like this. Okay, into little segments, and let each segment have some width. Let us keep it simple, constant width capital delta. Okay, that is how I have discretized it. Okay. Now, this charge that I had over here, the charge is sitting over here on the surface, as I said, as a one dimensional line charge, that is the unknown. So, what I do now is, this is the a little bit of a trick. This unknown function over here, I write it as the sum of n functions, each one with a coefficient a n and the function g n. Okay. So, what is this g n over here? I have written it over here. It is what is called a pulse function. So, what does this pulse look like? So, first of all, there are capital N pulses that I have used. The definition of this pulse is that it is 1 inside the nth segment and 0 everywhere else, right. So, if I were to plot this, so this is n minus 1 delta and this is n delta, right. So, this function is 1 over here and 0 elsewhere. Okay, and 0. So, for example, we can call this is your g n. Okay. Now, if I want to show you g n plus 1, what will it look like? G n plus 1, this pulse would be to the, will it overlap with the previous function? No, right, it will be to the right, right. So, if I draw this over here, let me just sorry. Right, so this is going to be g n plus 1. Right. So, the idea is clear what we are trying to do. We are trying to approximate this function in terms of pulses. So, it is, if I had a function like this, if this is the actual function, I am trying to make a piecewise constant approximation of this function, right. I am going to say this is how I am going to approximate my function. Okay. It is crude, but what it does is it makes our math easy, okay, and later we will see how to get a little bit more sophisticated about these things. So, these are the correct terminology for them are, these are called basis functions. Okay. So, we have chosen a basis function which are the simplest basis functions, pulse basis functions. Okay. So, we will call these as basis functions for what? For rho. Now, having done this, remember our unknown was this rho, which was a function. Now, I say that solving for a function is a difficult thing. Let me make my life a little simpler. Let me now solve for something else. So, when I converted from rho to this guy over here, what became my unknown? The a's, right. So, these now are my unknowns. So, unknown, and are they functions or just scalars? Scalars, right. So, which looks easier to you, solving for rho or solving for a? A, right. I just have to solve for a bunch of numbers, which is much easier than solving for a whole entire function. Okay. So, I plug this expression for rho into the previous voltage equation and out comes this expression. So, 4 pi epsilon I have taken up over there. The left hand side was originally 1 volt. So, that 1 multiplied by 4 pi epsilon naught is what I got on the left hand side, and the rest of it is as before. Okay. Now, we will go back to how we had decided we will solve this equation. So, to solve this equation, we had said that if you look back, if you remember what we did previously, we had said let us choose those points where I know the potential, and I chose those points to be along the axis of the wire, right. So, what we can do is there are n segments over here. So, for example, this is your y 1, right? No, let us not call it y 1, let us get rid of this. Okay. What I have n capital N pulses, right. That means there are capital N segments over here, okay, and my number of unknowns are n. Okay. So, what we will do is let us choose our the observation points, let us choose them systematically. So, let us choose the center of each of these n segments. So, for example, this let us call this the mth segment and let us call this y m. Okay. This the choice of the place where I evaluate the function, I also call it a matching point. Okay. Previously, the y primes we called them as source points, because that is where the source charges were, and the corresponding place where I choose along the axis I call them matching points. Okay. So, with this in place, what will happen is 4 pi epsilon naught. Okay. So, the first let's just open up this integral over here. So, the first will be a1. Okay. This integral will go from where to where? The first term 0 to delta, right, because g1 will be the first term, and g1 is non-zero only in the first pulse, first segment, and 0 everywhere else. So, in this limits of integration, it will become 0 to delta, right. What happens over here, gn, which is 1 for that part. So, I will have a dy prime, okay, and here what will I have? What will be the two arguments? So, first one, so y1 I have, right, okay. So, we can make it say ym, no problem, okay, correct. I chose some point over here ym. So, ym comes over here, and y prime is my limit variable of integration, that remains as is. That was the first term. Second term will be, now you can see the pattern, delta to 2 delta, because that is where the second pulse is non-zero, dy prime r of ym y prime. How many such terms will I have? N terms, right. So, this final term will have a n, this will be from n minus 1 delta to the length, the total length, and again dy prime. Okay. So, we just expanded the summation, that is all we did. Okay. This integral is of course going to be different, right. This integral and this integral, they are not going to be the same, because even though the function sitting inside is the same, but the integral will be different because the limits of integration are different. Okay. So, starting off with the idea of discretization, choosing the pulse basis functions, opening up the expansion, what have we arrived at? We have one equation in how many variables? N variables. And what are these variables? a1, a2 all the way up to an. Okay. So, you can see where this process is going, right. Here I have kept the matching point ym is kept general. Okay. So, but this keeping it general has given us a strategy that we can use to formulate I mean to get the solution to this. So, there are n unknowns, I need n equations, right. So, what we will do is we will continue this process for all the matching points. So, what matching points will we choose? We will choose these y's to be the center of each of these n segments. Okay. Since there are n segments, each segment has one center y1, y2 all the way up to yn. right. So, the first equation as before, what we will get is I will get a1 integral from 0 to this thing, and I have, sorry, there will not be this anymore because I replaced it by g, okay, and this will be y1 y prime, right. I have substituted the value of g to be 1 in that segment, right. Finally, I will have a n minus 1 triangle all the way to L dy prime. And I will repeat this for each of the matching points. Final matching point will be at the very end, right. So, at the very end what I will get, so again first term will be a1 0 to triangle or delta, first term, and finally the last term right. So, now what we have done is we have got n equations, n variables. Seems like something we can solve, right. So, if we do it systematically, all of these guys on the right hand side, sorry, on the left hand side can be made into a column vector, right. So, I can take all of these guys and put them into a column vector B, right, and you can see that all of these equations have the variables a1, a2, a3 all the way up to an in one string, right. So, that looks like what? The product of at least one vector, one row vector with a column vector. So, what should the column vector be? The column vector will be A's. A's will be the column vector. So, I can see, so this will be a column vector over here. So, that will be a1, a2 all the way up to an. Okay. The first row of this will be what? These terms, right? This integral, all of this, and there is a pattern to this. So, similarly, when I go to the next row, this is yet another, the mth row. So, all of that can be combined into one matrix, and the size of this matrix is n cross n. This is n cross 1, and this B over here is also n cross 1, right. So, I have rewritten this into, we can say A x is equal to B, where x is the unknown vector. Okay. So, this is going to be the objective of the approach that we will follow for all integral equations. Somehow get it into A x is equal to B, where A and B are known, solve for x. Okay. So, this is your thing, x is unknown. Okay. And you can see there is a very nice general pattern that is emerging for what is the mn element of this matrix A. So, m is coming from what? The mth matching point, right. So, mth is the matching point which corresponds to the row or the column. Which does it correspond to a particular equation or a particular column? The matching point. Equation, right. So, that is the row number, that is why it is a m n, right. So, this is coming from the matching point, and n over here talks about this, n over here is going from here all the way to the right, right. So, that is telling me the source point. Right. So, your matching point is over here and your source point is over here, right. I have kept it in general g over here in case we choose some other kind of function other than pulse. Okay. So, I have got a matrix element and I did not write it over here, but it is trivial to see what is B m in this case, the mth element of the vector B. What is it? 4 pi epsilon naught, right. So, this turned out to be really simple. In other problems, it will not be so simple. Okay. So, this sort of completes the description of how we arrived at a system of equations. So, what did you do? You took your problem, discretized it, chose a set of basis functions, then use those basis functions to expand your integral equation and convert it into a discrete set of equations, which finally gave you a linear system of equations, and you solved it. Okay. So, this you can ask lots of questions. How do we know what n to choose? That would be the first question, right? Should I choose n equal to 2, 3, 4? What should we do? As large as possible. Okay. So, larger the n, you can see intuitively the better I will be able to approximate the actual function rho. The price that you will pay, higher computational time. Okay. So, that is one obvious trade off for n. Also, this the expression over here for a m n that you can see over here, this is where you can use your Gauss-Legendre quadrature rules or any other quadrature rules to evaluate this matrix element. Okay. So, in this problem it is a very small toy problem, so it will not matter very much even if you choose an inefficient quadrature rule. But you can imagine in real life systems, let us say you are calculating the radar cross section of an aircraft, you will have close to 1,00,000 elements, right. And for 1,00,000 elements, if you are trying to evaluate this integral, the number of points you choose in your quadrature rule, the more the number of points, the more the number of function evaluations, and if I have to do this 1,00,000 times or a large number of times, or a million times or whatever, what will happen? Your cost of just evaluating the matrix elements itself, forming Ax is equal to b, is going to explode. So, that is why you need as efficient a way as possible of giving you this AMN to desired accuracy. So, that is the cost of making the matrix A. Then there is the second is the cost of solving Ax is equal to b. Okay. So, that involves another course on numerical linear algebra. I will just roughly tell you two things. There are two ways of solving Ax is equal to b. One is what is called a direct method, which you all have studied in high school. It is called Gaussian elimination. This works in sort of reasonably small size problems. The MATLAB syntax is very simple, A/B, right. That is what gets you your solution. The second is what are called indirect methods. Right. So, indirect methods are iterative methods. So, something called conjugate gradient method, if you have heard these words. There is a whole family of iterative methods which will not give you the answer in one shot. They will start with some guess and keep refining the guess. Okay. So, if the problem size is very, very large, you need to resort to iterative methods, and as the course goes, I will give you a little bit more information on these things. Okay. MATLAB also has these things inbuilt. Alright, so that is about the ways of solving Ax is equal to b, but let us get back to the first question which I asked you. How do you choose n? Right. So, you might start out conservatively, choose some small n, and then start making n larger and larger, right. So, I have some graphs over here. So, the first one is n is equal to 5, and what is being plotted is your rho as a function of, this is my y axis. Okay. So, I just chose 5 segments. What will be the size of my A? 5 cross 5, right. I solve it, I get the solution, and this is what the charge density, this is what it looks like. Intuitively it makes sense, the charge is tending to bunch up towards the end. There is of course at the center it is not 0, it is not gone to 0 because the charge, it will still be there. Right, as you said rightly in the start of the lecture, there will be some sort of a equilibrium that will be established where the forces are in balance. Okay. So, this was for n is equal to 5. As we went further to n equal to 20, what happened? You see that the solution is beginning to look a little bit smoother now, right. Here there were big jumps over here. Now, the jumps are, there is still one big jump over here, but these jumps are now smaller. So, I am able to approximate the function better, and this was for n is equal to 20. Again, it will take hardly a fraction of a second to solve this. So now this sort of brings the question, how do I actually choose n? So one popular way of doing it is that you take your, so let's say your solution that you got at resolution n, okay. Now let's say I increase from n, I go to a larger number m, okay, where m is greater than n. What I can do is I can find out the relative change. So x, okay, this is just the difference between the two. I can take the norm of this vector to find out how much energy is in the difference, and I can find out, for example, compared to the reference solution, what is the norm. So these, when I say norm, I am taking the 2 norm of the way. So xn is the solution obtained when n segments chosen, okay, and xm therefore is the solution with m larger number, larger than n chosen, okay. Now I can say that this relative change over here should be less than, let us say, some epsilon. This epsilon can be something like 0.1 or 0.01. So you can say I want my solution to stabilize or converge within, say, 1%, 5%, whatever, depending on your requirement, okay. What you will find is, as you begin increasing n more and more and more, at some point your cost of computation becomes very large, but your improvement in solution becomes very less. So you're past the point of, you're getting diminishing returns. So at that point you should stop. So the systematic way is to implement inside your solver something like a check on the relative change in solution, and stop when this threshold has been met. Then you can be sure that, okay, the solution has converged. So the word for this process is called numerical convergence. Okay. Again, this is a key strategy we will use throughout this course in solving systems of equations. Right. Is it fine? Okay. So that is one way of increasing the accuracy, increase n. Any other ways that you can think of improving accuracy? Looking at the solution that I have obtained, can you think of some other cleverer way where I can keep n small yet get a more accurate solution? Basis functions can be chosen little bit more intelligently, right? Here my basis functions were pulses, so I was forced to approximate my smooth function by a set of pulses. That's why I need large number of pulses, right?